we'll get started with our yesterday's discussion, variation of stresses at a point. Yesterday we discussed that there are two ways of normally finding out how the stresses vary with inclination. So let me get my small letters. So we have got a element so at a certain point we have a stress, and this is our element, and what we are saying that this element can have any orientation. At this point we know that there is some stress, existence of some stress, okay, and so we assume that those stresses are described by the shear and axial stresses at each and every face of this element. Then our aim is to find out what will be the inclination at which we would have maximum axial stress and shear stress. That's what we are trying to find out. Okay? Stress flow is a complex phenomena within a structure. Okay, and for our convenience, we say that we divide a structure into small boxes, and every box has got stresses at its face, mainly two stresses, one axial and one shear. So if we pick up a random point at in a structure, okay, a random point in a structure, this is our structure, and we pick up one random point anywhere. And at that point we say that we want to study stresses. So we assume that there is a box, and that box has got stresses, I mean the pair stresses, which is axial and shear at every face. And if we rotate our box, okay, so we keep on rotating our box and we are trying to find out at which inclination we will have maximum stress. Okay, so normally how would we find out the point within a structure which can have maximum stress? Mainly, you know where the maximum moment is, okay, you know where the maximum axial stress is. So if a point which has got maximum moment, that will normally give you the maximum stress. Like for example, in this structure, which is L-shaped structure, if I've got a load applied like this will, okay, so you can draw the bending moment diagram of this frame, and based on the bending moment diagram you will find out that this point, this joint is carrying maximum moment. In other words, this has got maximum stress. So you pick up that point, that box within this area, okay, and then when you pick up this particular point, then you draw it over here. Okay, and now these equations will tell you how to rotate at which inclination should you get the maximum axial stress and shear stress. Okay, so that's the use of this equation. Okay, so first normally you draw the axial force diagram, the bending moment diagram, and the shear force diagram. That will give you the maximum stresses in the structure, the location where you will get maximum stress. From that particular location, you pick out that box and draw the stresses. Okay, how would you determine those stresses? That is normally determined in a lab. Okay, or you can use some software to determine it, I mean carrying out structure analysis. But anyway, in general, if you don't have any software, so you go to the lab, carry out the experiment, and you find out the strains in that particular area. That strain, when multiplied with E, you will get the stresses. Okay, so for the axial stress you multiply it with E, for the shear stress you multiply it with G. Okay, so you get your D stress profile. Now once you have got that stress profile, now the point is, those are the points which you have determined in the lab and where you have placed your strain gauges. Okay, so those are not necessarily the points which are giving you the maximum stresses. The maximum stresses will be at some inclination, and you have to rotate that thing okay, to find out the maximum stress. And that's why we are having these arguments since last 2-3 lectures, that how to find out that maximum. So two methods. One was these two equations. You derive it. Okay. You take maximize them, both of them. Okay. Which means that you differentiate that with respect to thetas and equate it to 0. You get the theta, the maximum inclination, where and from there you plug it back in these equations and you will get the stress and the tau. Okay, which will be at certain inclination. So that is one way of doing it. The other way is the Mohr circle, okay, which is a bit easier way. And how do we draw Mohr circle? I told you, you take these two equations, okay, you square and add them up. We square them and add them up, and that gives us the equation of a circle. Now this is the circle. You draw this circle. Now please note that you have got stress and tau as variable. The other parameters are all known. Stress x, stress y divided by 2. This is actually the stress which you already know, which either you will be given or either you would have found that in the lab. Okay? Tau xy is also, or tau yx, that's also known to you. What is not known to you is the maximum one. Or if you are interested in finding out the inclination at a particular inclination. Okay? Stresses at particular inclination if you are trying to find out. So that is not known to you. So once you get that, this is your centroid. You draw a circle. For circle you need two dimensions, two variables. Okay? So you draw the axes. One is stress, another one is tau. So this is the same thing you have done in your previous classes, like x and y. If you are given, okay, you draw on x-axis, y-axis, you have the equation of circle, you just draw the circles. And what do you need? You need the centroid and you need the radius. So that you can easily get from this equation. And you can easily, nicely draw the circle. Now please remember that this is the centroid. Okay? This is the centroid, which is stress x plus stress y divided by 2. Okay, the centroid is located at this distance. Now, once you have drawn that, after this, we have to establish a convention. Okay, naming convention, the sign convention. So the sign convention, I mean, you can have any sign convention. The most common one, and the common one is that tension is positive. And clockwise shear is positive. So any face which is causing clockwise shear and which is causing tension, that is positive. Now this is the element which is known. Okay, see over here at this point, we have stress x as positive. Stress x is positive, and this shear is causing clockwise. Look, this is rotating, trying to rotate it in the clockwise direction. So these two are positive. So I have taken this point as stress x and tau yx, which is positive. Yes. Now after this, we have to draw the other face, which is tau yx, which is this one at the y-axis. Okay, the y-axis face we have to draw. Now please remember that on the Mohr circle, whatever you draw, that should be at 2 theta. And in reality, that is theta. In this diagram, that should be represented as theta, and in the Mohr circle, that should be represented as 2 theta. Why? Because based on this equation, the Mohr circle equation is drawn based on cos 2 thetas. Okay, so whatever inclination you take over here, that should be 2 theta. But when you are then showing it diagrammatically, the inclination of the plane, that would be theta. Okay, so this is an important thing to know. And I told you that what's the reason? The reason is that this equation is derived based on 2 theta. The Mohr circle equation is derived based on 2 theta. That's why when you are moving your diameter, okay, so you move it by 2 theta, and in the real element you are actually moving that by theta. Okay, so the theta orientation of this is equal to the 2 theta orientation in your Mohr circle. Mohr circle is actually telling you, is giving you an infinite number of the stresses and shear at different orientations. Okay, so this is like a, so what we are saying is that the Mohr circle at every point, if you draw a tangent, this tangent at a particular point represent face of an element. So there is an element, this is an element, okay, this is an element, and that, this is the face. The Mohr circle is telling you what is actually the orientation of this element, which looks like this. Okay, so this element is located like that according to Mohr circle. Your radius is normal to the face. This is the face. Please know, this is the face where you have the stress x and tau by x. When you are drawing it on the Mohr circle, you pick it up and you rotate it. You rotate it on the Mohr circle. Okay, you rotate it on the Mohr circle, and it will give you different orientation of this element. Are you guys with me? So in other words, you are actually rotating it like this element. Okay, but in Mohr circle, you are rotating this element, okay, along the Mohr circle. But please remember, if I rotate this, okay, like this will go by 2 theta, but in reality in this element it will be going by theta. Okay, I am again and again saying that. Why? Because people make that mistake, students make that sort of mistake. They get confused with the theta orientation of this and the 2 theta orientation in the Mohr circle. And I am again telling you that this is because that this formula, which is used for derivation of Mohr circle equation, that is using 2 theta. Okay, so you move this 2 theta, and in reality this would be theta. Okay, so that is your Mohr circle. Now Mohr circle will give you different types of planes. Two very important planes are those ones. One of them is that well, let's put it differently. There are 2 important planes which we are normally interested in. One is that plane where maximum stress, axial stress occurs, and one is that plane where maximum shear stress occurs. Mohr circle give you a picture that it's not necessary, or it's not possible that where your axial stress occurs, shear stress will also occur. Okay, and you can see that. Look at where is the maximum axial stress occurring according to Mohr circle. Maximum axial stress. Maximum axial stress is on this axis. Okay, you have got one and you have got another one. Please, so that means that at this axis there is no shear. So wherever you have maximum axial stress, okay, at that plane you won't have any shear. That is an important point to note. Okay, another thing which you must appreciate is that the Mohr circle has got one radius and another radius. This one radius is giving you x-axis. Okay? In this diagram, in reality, you have got x-axis in this axis and y-axis is at 90 degree to this axis. Please note, y-axis is 90 degree to this axis. However, in Mohr circle, this is x-axis, but I told you that y-axis should be 2 times theta, 2 times 90, which is at 180 degree to this one. So x and y axis are shown at 180 degree in the Mohr circle. In reality, they are at 90 degree. That is an important point to note, and that is obviously supplementing whatever I have been telling you. I think so 4 or 5 times now I have told you that this is an important, that your theta on the element, within the element, is equal to 2 theta on the plane, on the Mohr circle. So the Mohr circle gives us the maximum stresses in that location, in the location where your where the shear stress is 0. This is called principal axis. The axis is called principal axis. Okay, why do we call it principal axis? Because this gives you principal stresses, the main axial stresses. And just to demonstrate, okay, for demonstration purpose, imagine I have got an axis which is purely shear. Where will that axis be according to the Mohr circle? Which is purely shear, no axial stresses. The purely shear one is this is the shear stresses. Okay, at these two axes you will have shear stresses, but there is an axial stress also. At these two axes you will have shear stress and you will have axial stress. Okay, in this scenario, if you draw this axis which is vertical, you can see there is a shear stress which is this one, but there is axial stress also, and the axial stresses both are positive, that means tension, and both are equal. Can you see that? This is, I've drawn now my Mohr circle and I've drawn this vertical. This is, I told you, this is my x-axis and this is my y-axis. So if you draw vertical line, okay, so over here your stress is equal to stress over there, isn't it? And the shear is opposite. Okay, so this is the, so at the point of maximum shear stress, you in this case have axial stresses. There is a difference, please note, I'm again repeating. At the principal stresses axis, you don't have any shear stress, but at the maximum shear stress axis, you have axial stresses. What will happen if this Mohr circle which you drew came out to be over here at 0? When can you have that at 0? When stress x is equal to minus stress y. If you have a case, you can have any case, okay? If your stress x is equal to minus stress x or minus stress y, yes, these two will cancel out and your Mohr circle will come to this point. Now if you take your shear, your stresses would be 0. Okay? In this case it's not 0. But if your centroid C is 0, then your shear stress is 0. So I can demonstrate that to you, that how is that 0? Look at that. Imagine your Mohr circle is at the origin. If it is at the origin, that means that you have only shear. So I draw only shear. Okay? When I draw, this is the shear. Okay, this is the shear, isn't it? Only shear. Only shear. So what's happening? You have another box where you have principal stresses, only axial. See? Only axial. This was initially a box. It stays like box. So there is no shear in this rubber band. Look at the rubber band. Okay? In Mohr circle, I've got the plane which has got only shear. So I have this box, this rubber band, and this rubber band is showing that they still remain perpendicular to each other. The sides remain perpendicular. That means there is no shear stress. It's only extension and compression. And you see, if I draw my Mohr circle, I draw it down. If I draw my Mohr circle like this, for example, yeah, what do you have? You have at the principal axis, you have one positive, which means tension, stress, and one negative. And they both are at 90 degree in the Mohr circle. So in reality, they are at 45 degree. I'll repeat. If we have a Mohr circle drawn taking this origin as center, okay, and that would happen if my C is 0. So the element which has got maximum shear stress, okay, which at that point, at that axis, I will have 0 axial stresses. Okay, so why? Because this is drawn at 0, so I have 0 axial stress. Then from that axis, if I want to find out what is my principal axis, where I have got only axial stresses, that axis is located at 90 degree in the Mohr circle. And I told you that in reality that is at 45 degree. So you see, that is backed up by this model. Look at this now. I'm moving it. This is the shear. Okay? And this box is at 45 degree to this face. This is at 45 degree, not 90 degree. So in reality, this is at 45 degree. But on Mohr circle, it is at 90 degree. And it is true that when you have a shear, okay, on one axis, the principal axis, will have axial stress and one tension, one compression. Tension and compression. And that's what you can see over here. You have got tension and compression. So my point is that Mohr circle, if you understand it, you can interpret lots of things using Mohr circle. Okay, so in exam, normally I will give you one element and I will ask you to find out element at another inclination. So which means to say that you will draw the Mohr circle and then you move it and you find out element at another inclination. So the inclination which I give you, for example, that is theta. So you will multiply 2 with that theta while drawing Mohr circle, and you will find out the stresses in that, and you will get me the stresses. Now, if in the same case I want you to find out what is the principal axis, give me the principal axis. So the principal axis is located at 2 theta from this one. So this is, okay, so this is located at 2 theta. So this principal axis is located at 2 theta from this axis. And so you have to find out what 2 theta is. What is this angle? That angle you can easily find out. You know the radius, you know this one, so you can find out this angle. So how much should, so by what angle is this principal axis? Okay, so this is at, so let us see by how much should you rotate this. Okay, so you have this thing and you have to rotate it like this. So in other words, you have this one and this is getting rotated clockwise, yeah, by 2 theta. So that means that you have to rotate this by theta clockwise. So it will be like this. So your principal axis will look like this, and this will be located at an angle theta. This is positive, this is also positive in our case, assuming. So that means that you have axial stress like this and axial stress like this. So this is the inclination of the element which is based on your principal axis. Okay, so I have taken and I have rotated it. I have rotated it and I get this one. Okay, so it was 2 theta. This I have to rotate by theta, which gives me this thing. So this is the orientation of the element where you will have maximum axial stress. If you are asked to find out the maximum the plane having maximum shear stress, so you have to then rotate it in the counterclockwise. So counterclockwise would be like this. So you rotate it. So this is like this, and you rotate it like that. Okay, and that element you just find out all your stresses and your shears corresponding to each and every phase. That will be the plane of maximum stress. If I tell you find out the stresses at angle 30 degree from this axis, clockwise, for example, clockwise 30 degree. So what you will do is you will over here you will go 60 degree. 2 times 30 is 60, and at that 60 degree you will find out the stress x star by x and corresponding that, okay, the corresponding negative, the perpendicular one, and then you draw your element. So it's a pretty straightforward stuff, but the important thing is that you should understand the concept. Any question? It's okay?